Welcome to the fourth lecture on topology and condensed matter physics course. We have been talking about discrete symmetries and how these symmetries actually are responsible for the topological phases of matter. And if you actually destroy one of the symmetries, then the system may not remain topological or may make a transition from one topological state to a trivial state or a topological state to another topological state, which will happen via the gap closing of the energy spectra of the Hamiltonian. Okay. So, while we were discussing the discrete symmetries and we have talked about these time reversal symmetry, which has been discussed in the previous day, and we have done it for both spinless systems, that is the Hamiltonian does not explicitly involve spin, or even in the case when it does explicitly involve spin, because if particularly if the system has this spin orbit coupling, then you need to take into account spin degrees of freedom, else it can be considered as spin polarized, which are both the cases we'll see over as we progress through the course. All right. So, now since we have done this time reversal symmetry, the one that's remaining, a few of them are remaining, we'll now talk about the inversion symmetry. This is also called as parity. So, what's an inversion symmetry? If you change x to minus x or r to minus r, then that's called as inversion symmetry. I mean, r to minus r, what I mean is that, so the vector r goes to minus r. That means the magnitude r remains same, theta changes by certain angle and phi changes by certain angle, and that's what is called as a parity operation. This you might have learned when you did hydrogen atom and or the angular momentum. So, in fact, you wanted to know that what are the sort of inversion symmetry or parity of the spherical harmonics, and the spherical harmonics actually pick up a minus 1 whole to the power L under parity transformation. So, this is like minus 1 whole to the power L YLM. So, this theta phi, and so this is equal to theta plus pi and phi minus, so it's probably minus here or plus here. Anyway, this can be settled if you look at the relevant discussions in hydrogen atom. Here we are talking about discrete symmetries, that is under these transformation, let's talk about this parity or the inversion symmetry operators by a pi. I stands for inversion and P stands for parity. Why I am writing both the with a subscript is that we'll also use the particle hole symmetry with P. That's why I'm just writing it with a pi. So, if you have a pi acting on R and a pi, so this is a dagger, then this becomes equal to minus R. So, R is the position operator. So, this is the definition of that. So, in a simple case, pi could be just a matrix like minus 1 0 0, 0 minus 1 0 and 0 0 minus 1, which inverts all the R to or the x to minus x, y to minus y, and so on. Okay. So, if you write it like that, then PIR, these are unitary operators, which means that u dagger equal to 1. So, pi dagger equal to 1. So, this becomes equal to minus r p I and so on. So, what I do is that I write multiplied by the pi dagger on both sides, and the pi dagger becomes equal to 1, and that tells you that I mean this, or what you can do is that you can also write left multiply by p. Let's just do that instead of this step. So, I'll write it. So left operate by pi, and that will become RPI, because pi dagger will become equal to 1, and minus pi r, and so that tells you that they anti-commute because RPI plus PIR equal to 0, and hence they anti-commute. So PI and R anti-commute. Okay, and what happens to the momentum variable? In fact, we mostly talk about the position variable, momentum variable, and if it concerns spin. Now, of course, parity has got nothing to do with spin, so it will leave it unchanged. So this is for the real space operator R. And for the momentum operator P, it has a very similar thing, because P is nothing but dr dt, which means that it's proportional to the velocity multiplied by the mass. So this will also give rise to this Pi, then P, and then Pi equal to minus P. Okay, and so the P is the momentum operator, and then again we have these Pi and P that anti-commute and will give to 0. This is what it means by when a Hamiltonian has P and R. The Hamiltonian contains P and R, and this is individually how the inversion operator or the parity operator acts on each of R and P and will transform them. So if Hamiltonian has both R and P, so you can check whether it changes sign under this inversion operation. So let me write down a few important points. So if you consider say a 2D block Hamiltonian, just for an example, what I mean by 2D block Hamiltonian is that it's a H which is a function of K, and K is a function of Kx and Ky, just a 2D thing. And if it is symmetric under both inversion, which is what we have seen just now, and time reversal symmetry, in short I'm writing it as TRS, which is T, then the inversion of course maps to, so Pi maps K to minus K. K is nothing but the wave vector, which is related to the momentum by just multiplying it by H cross. And it also satisfies that P square is equal to 1, okay, because if you do the inversion twice it comes back to the same configuration. And then if we have TRS as well, then it sort of so TRS does the same thing. So TRS also maps K to minus K, and T square of course will square to 1 or minus 1 depending on whether we have the spin variable in the problem or not, because the spin is not included here explicitly as we can see in this block Hamiltonian, then we can write it as T square equal to plus 1. So if a Hamiltonian has both T and Pi, okay, then H of K remains as H of K. I mean, so they will remain invariant under this both time reversal and the inversion operation. Okay. So let me now look at, in brief, we'll talk about it. We'll talk about the particle hole symmetry. So, this means that if we convert a particle into whole, then the Hamiltonian, whether the Hamiltonian remains invariant, it's a property of a superconductor to have particle hole symmetry. Okay, so the number of particle states will correspond to exactly the same number of hole states and so on, and corresponding to a particle of energy E, particle state of energy minus E, there will be a whole state of energy plus E and so on. So, let's write a PHS. Let's that the operator be for the particle hole symmetry, and then a Hamiltonian will have this kind of operation which is minus H. Okay. So, this is the symmetry operation of that. So, we can write down this PHS usually as a sigma x and a k, where sigma x is a Pauli matrix which is written as 0 1 1 0, and k is the complex conjugation operator. Okay. And as I said that this is inbuilt in the case of the superconductors. Now, to wind up the discussion, we will talk about the chiral symmetry. This is a very important symmetry of the Hamiltonian and vis-a-vis its relation to topology. And in a very simple model which we are going to see just after this discussion, say a model has like for example graphene has a chiral symmetry, which means that both the A and B sublattice they are like this. So, it's a honeycomb lattice, and there are two unit cells, two atoms per unit cell, and both the atoms we name them as A and B, but both the atoms contain carbon. So, if A changes over to B or B changes over to A, it's like an inversion about this dotted line. Then the Hamiltonian remains invariant because both of them correspond to carbon atoms. Okay, this is a particular example in graphene, but we'll see more examples, particularly tight binding Hamiltonians. And at this moment I do not want to elaborate on it much, but a similar operation which we do it by tau. So, this is a chiral symmetry operator. It has a similar effect as the particle hole symmetry. So, this is equal to minus H. Okay. So, this is the operator, and these are how it sort of transforms. Now, I am just saying that chiral symmetry for a very simple case is the inversion symmetry, or it's a this is called as a sublattice symmetry. So, the chiral symmetry for graphene is a sublattice symmetry. What graphene is we haven't said yet, but we will make that clear as we go along the course, and of course all these symmetries are unitary symmetries or anti-unitary. So, these gamma dagger is equal to 1 and so on. Okay. So, these are some of the discrete symmetries that we will be needing in during the course, and let's now go into a simple problem which is a tight binding model that shows topological features, and it's the simplest paradigmatic model for seeing topology and is widely studied in this context. It's simple, and as well as it's quite intuitive for us to understand. Okay. So, we'll do that, and but before that let's do a quick recap of the tight binding Hamiltonian or tight binding model. And to understand what that is, it's a method of calculation of the energy spectrum for a particle that is subjected to a periodic potential. And what I mean by periodic potential is that we talk about crystal lattice where there are presence of ions or atoms at regular interval, and this regular interval is called as a lattice constant. Okay, and as if I consider an electron to be moving in this array of ions or atoms, these ions, say for example, are going to sort of exercise, or the electron will actually perceive this interaction or rather a potential due to this presence of these ions or the atoms. Okay, and since these are periodically placed, one can write down V of R equal to V of R plus capital R, where capital R is the vector that connects from one lattice point to another. Okay, so this is the R, this is equal to, if you write, so R vector is equal to A, say R cap or something. Okay, so this direction is R, or you can write it simply as X cap. Okay, so this is called as a periodic potential, and Bloch has said that the wave function of a particle is subjected to such a potential has a form which is psi k of r, this is equal to u k of r exponential I k dot r, this k is a vector. So where is the periodicity information embedded? The periodicity information is embedded here in this u of k, which is equal to uk of r equal to uk of r plus r. Okay. Now this is well known, and the proof is also quite simple and straightforward. We will not follow that. This is the first course of solid state physics would teach you that this is the wave function, but just getting the wave function is not enough to arrive at the solution of a problem. We also need to know the energies. And in order to get the energies, we need to resort to some approximations. And tight binding approximation or tight binding model is one such approximation, in which it is assumed that the electronic wave function is tightly bound to this these ionic cores. I am just for a moment I am consider them as ions, so that the electron feels a potential. It could be an atomic potential also, but let us just consider that there is a potential like this, that is an attractive potential given by these ions. So these ions are positively charged, and then it gives a potential which is given by this. Let me use a color so that overwrite on this. So this is the potential in red that you are seeing. So an electron that's going passing through these potential. So the electron will be passing like this, and it sees a potential, a series of potential which are periodically placed, which means they are placed at regular intervals, which are given by this A, which called as a lattice constant. Okay. So the assumption is that these electrons are they have the majority of the amplitude of the wave function is centered at the core, ionic core, that is, it peaks here where the ion is, and so on at all of them. It has very little overlap between the wave function at the next core as the next ionic core. So you see this region of overlap, and this region of overlap is very small, and that is why it is called tight binding. It is tightly bound to the ionic core, and these small overlap renders a mobility to the electron, because the electron has to go from one ion to the next ion and to the next ion. It will move around. It is a mobile charge. So it is tightly bound to this, and in this approximation one can work out what the energy is. As I said, that the energy is still missing into this Bloch's theorem, which gives you the form of the wave function. Okay. So, H is in this particular case, H is equal to say for example a p square over 2m, which is coming from the electrons, and plus a Vi. Okay. And so, this can be written as the kinetic energy plus the Vi, where Vi are these ionic potentials at a site I. So, I equal to 1 to n, whichever the number of sites are. Okay. And one can write down the wave function as psi k, and it can be expanded in the basis of phi alpha. This is equal to Ck and a phi alpha. Okay. So, this is like a expanding it in a complete set of states where phi alpha is the basis. Okay. Psi k obeys Bloch's theorem. So, I am trying to give you a very simple derivation of the tight binding Hamiltonian, and which is going to be essential for a lot of the discussion that is going to follow. And phi alpha of course are the basis states. So, if we write down the matrix elements of the Hamiltonian, that is H alpha beta, where alpha and beta are two orthogonal bases, phi alpha H phi beta, we have already written H, and this is equal to a phi alpha k plus Vi and a phi beta. Okay. And this is so the kinetic energy is a one body term which we have discussed. So, this can be written as the atomic energies. So, let us write it as epsilon AT for the atomic energies, and what is important is this term to calculate, which is equal to I and a Vi phi beta. Okay. This is basic quantum mechanics. So, these epsilon AT are the on-site atomic energies, basically because of the kinetic energy of the electrons. And this is the thing that one needs to compute, and one can make an ansatz as follows: phi alpha sum over I Vi and a phi beta. So, this is equal to V0 for alpha equal to beta, it is equal to minus T for alpha equal to beta plus or minus 1. We are talking about one dimensional system, and it is 0 otherwise. Okay. So, what I mean is the following, that the matrix element for this Vi will vanish if these I and j or rather these alpha and beta are not these wave functions that correspond to the neighboring sites, and at the site for alpha equal to beta, that is the on site, that term can be of course absorbed in this epsilon AT. Okay. And so, if we leave these epsilon AT and V0, which we can all combine, that is we can write down H alpha beta equal to some epsilon 0 delta alpha beta, and then we can write down a minus T. T is the amplitude for that matrix element for which alpha equal to either beta plus 1 or beta minus 1, where alpha and beta here refer to, of course, they refer to the basis indices, but the basis is written in terms of the on-site indices, the site indices for the system. So, this is equal to delta alpha plus 1 beta plus delta alpha minus 1 beta and so on. Okay. So, and where epsilon 0 is of course this epsilon at plus a v0. Okay, that is a constant that we do not need to worry about that. Anyway, this gives you the diagonal elements of H alpha beta, and minus t they lie on just the band above the diagonal and below the diagonal, and this is the form of this Hamiltonian, and the energies are these are basically nothing but the energies, and these energies are obtained within this tight binding approximation as this. So, this is the tight binding approximation, and this is the energy corresponding to that. So, when I write down H alpha beta, which means that I am writing down the matrix elements of the Hamiltonian. Okay. So, this can be written as, so your psi k H psi k, which gives you the energy, it can be written as alpha beta exponential minus I k r alpha. I am writing it as a vector, but in one dimension it will be a scalar. So, phi alpha H phi beta and exponential I k dot r beta. So, this is nothing but equal to sum over alpha epsilon 0, which takes into account the delta alpha beta, and a minus t exponential I k a, where a is equal to r alpha minus r beta. So, this is I am writing it in one dimension. So, in 1D it becomes just a. So, a is the magnitude of this, okay, plus exponential minus I k a, that comes from, so this alpha r alpha minus r beta, and if you leave this term, which is just a diagonal term, then this becomes equal to minus 2t cosine k a. That is the tight binding dispersion for a 1D lattice. And very soon we are going to use this. So, in 2D square lattice, so this is the 1D chain result, and so this is like epsilon k, that is its dependence on this k. K is a wave vector that runs over the first Brillouin zone, and this is equal to minus 2t, and then you have a cosine kxa plus a cosine kya and so on. Okay. In a 3D cubic lattice, this can be, it is a simple cubic lattice. So, epsilon k will be minus 2t cosine kxa plus cosine kya plus cosine kza. Okay. And in all these cases, the k x, y, z, etc., they run from 0 to 2 pi. Okay. They are sort of in this interval, or you can call it a minus pi over minus pi to plus pi. Okay. So, this is a simple tight binding model that gives you the energy of the electrons in a periodic potential. The wave function of the electrons, they have already been given by the Bloch's theorem. Okay. So, we are more or less ready to treat a tight binding Hamiltonian. The main motive of us in this particular course is not to look at the electronic dispersion and talk about transport properties, etc., but to look at the topological characters from these dispersion. And a priori, without doing any calculation yet, we can say that these topological properties are intimately connected to the band dispersion or the spectral dispersion, that is they are embedded into this epsilon k. So, if you change the epsilon k somehow, if you do some band engineering, or if you change say you put say for example an alpha here, okay, where alpha is varies from 0 to 1. So this alpha, and let me write it with a different color. I do not intend to put it, but just in case that you have an anisotropic dispersion for some reason, then these alpha will go from say 0 to 1. So, alpha is 0 to 1, and you can clearly see that if alpha equal to 0, it becomes a one dimensional chain, and for alpha equal to 1, it becomes a regular 2D square lattice. Okay. So, any non-zero value of alpha, that is between 0 and 1, it will correspond to an anisotropic dispersion in which the bands will be deformed. If you draw the bands between minus pi and plus pi, or 0 to 2 pi, then the bands will be deformed. Okay. The standard way of doing this is that you take a kx and ky. So, this is kx and ky, and you calculate this quantity, which is minus 2t cosine kx a plus cosine ky a, and then plot that in the the z direction. Your epsilon k is in the z direction, and then when you take the projection onto the kx ky plane, will give you the contours or the energy dispersion, and this dispersion can be represented by colors, which will show the color will code values that are either higher or lower depending on the variation of the dispersion. So, coming back to the point that if you change alpha, or you somehow deform the band structure by some chemical pressure or some mechanical pressure or something on a lattice, then the topological properties are bound to change. And these topological invariants that we have talked about at length, they also will change. Okay. So, let me show you one very simple paradigmatic model which is called as a Schuh-Schrieffer-Heeger model. Okay. This is widely studied in the context of topology, and it was pretty long back, more than 40 years back. It was proposed in a paper by Sue, Schrieffer and Heeger. Schrieffer is the same one who's in the BCS theory of superconductivity. So, this is in Physical Review Letters on 18th of June 1979, and it is about these they say that these long chain polyenes, which are polyacetylene, and they have this form C2H2N, and this is how a long chain polymer, that is polyacetylene molecule, would look like. This C2H2. So, you see there is a double bond here, and then there is a sort of single bond, there is a double bond, and then there is single bond, and so on and so forth. Okay. And each of the carbon is attached to via single bond to a hydrogen. For us, it is not important, the hydrogen is not important. For us, what is important is this carbon bonds. So, if we forget the hydrogen for the moment and only look at these carbon chain, and carbon is in the, it has carbon has 1s2, 2s2, 2p2, that is a 6 electrons, and then these one of the p electrons that are available for conduction, and the other p electron, they sort of give rise to the sigma bonds, which is to the stability of this long chain polymer. Okay. So, it is, you can take it as 1 electron per atom, and 1 electron per atom should be a metal, because the electron is allowed to move from one carbon atom to the next and to the next, and so on, and will give rise to its conducting behavior. However, what happens is that these bonds are being probed by NMR spectroscopy. And when they are probed, they show that they have different length, this 1.36 angstrom and 1.44 angstrom. Okay. So, they have these double bonds have different length as compared to the single bonds, and these lengths being different, as a physics a person trying to find out the properties of this model, one can actually say that this corresponds to a hopping T1 and this corresponds to a hopping T2. Just to remind you that this is the same T that we are talking about, the T here, which is the hopping amplitude or the amplitude of the kinetic energy for the electron to go from one ionic site to the next ionic site. So, this is the same thing here we are talking about. So, there is a T1 and a T2. So, this model consists of 2 atoms per unit cell, 2 carbon atoms per unit cell, and T1 is intra-cell hopping and T2 is inter-cell hopping. Okay. Now, as it is, there is no surprise in this model, or the properties do not seem to be anything very different or would yield any topological feature that we are interested in, but it does. It when you tune T1 with respect to T2 or T2 with respect to T1, you see that the system makes a transition from a topological state to a trivial state. And once again, I want to remind you that the topological state is like the donut, and the trivial state is like the orange, and the difference between them come from the fact that one has a hole, that is a genus which the donut has, and the orange has no such hole, and that it denotes a trivial state of matter. So, whether T1 greater than T2 or T1 less than T2 will give rise to such topological state or trivial state, it cannot be a priori figured out. So, that is why this model is interesting. It is a model in 1D tight binding chain, and that is the simplest one can think of. And then we will see that depending on a topological invariant called as a winding number, this model shows different properties. So, the discussion is like this, that we will write down the Hamiltonian in the real space, which we have written it down, and then of course, we will Fourier transform it and take it into momentum space, calculate the energy, plot the energy, find out the topological invariant, which is the winding number here, plot the winding number, and see that the system winds here it is called as an exceptional point, but we have introduced this as a singularity. So, that point of singularity, whether your system is it encloses or not, that will decide. If it does, then it is a topological state, and if it does not, it denotes a trivial state. Okay. So, I write down so this is the intra-cell hopping. So, these carbon atoms that you saw there, they correspond to A and B sublattices. This is a C and a C carbon atoms, but since it is a 2 atoms per unit cell, that is why we have labeled them as 2 different sublattices. So, A and B are sublattice degree of freedom. Okay. So, this is the intra-cell term, that is inside a cell from A to B sublattice. So, N is the unit cell index, this is the unit cell index, and this is within the cell hopping of the electron from one carbon atom to another, and this one is the inter-cell hopping, okay, which comes with a T2. This one comes with a T1. So, which means that this hopping is T2 and this hopping is T1, and this is precisely we have said about that polyacetylene molecule, long chain molecule, and this is there the Hermitian conjugate. This is the Hermitian conjugate is always used in such tight binding models, and if you do not use the plus Hermitian conjugate, then the Hamiltonian will come out to be, or rather the energies will come out to be complex. So, there is a T1 and there is a T1 star for the Hamiltonian, which means that H equal to H dagger, your T1 equal to T1 star and T2 equal to T2 star, which means their Hermitian these things conjugates are same. All right. So, you have no term along the diagonal, because you see no term that connects, there is no potential at the on-site potential, and these are between the same unit cell. This is the hopping, okay, between A and B sublattices, and this is the hopping that is between this, and this is the hopping which is T2 and T2 star, and so on and so forth. Okay. So, this is written in this the first line indicates the Hamiltonian written on the side basis, and in the second term we wanted to make sure that you know how to write it in the basis which are formed by these site operators. So, C1 dagger, C2 dagger, C3 dagger, Cm dagger are the creation operators for electrons at the sites 1, 2, 3, 4 till m, and similarly C1, C2 here they correspond to operators, annihilation operators at the site C1 to Cm. There is, you have to be careful, if you keep m to be an even number, then you use the Tm minus 1 is equal to T1, and if you take m to be an odd number, then the last one that is or the one that is one before the last but one hoppings will change accordingly, because you want to end it at the with the right kind of hopping. All right. So, because this system has translational invariance, one can do a Fourier transform. This is the operator for the Fourier transform, where so there is n here, and then there is a alpha here, there is a n is the site index, if this is n, alpha is the sublattice index, and it yields when you do that, apply it to this Hamiltonian equation number 1, let us call it equation number 2, then you get a Hamiltonian which is like this. So, if you apply 3 on equation 3 on equation 1, then you get this, you get a nice and compact form for the Ck alpha, H alpha beta, K Ck beta, where H alpha beta has a nice form which is like this off diagonal form, that is, it does not have any diagonal term. 0, 0 are the diagonal elements, and the off diagonal elements has a real term and an imaginary term, and these off diagonal element is actually the complex conjugate of that. So, in the sense that if you change H alpha beta k is equal to H beta alpha, this and so on. Okay, I mean, I can write this as H alpha beta star and a transpose. Okay, so this tells you that it is a Hermitian matrix, and so I write f of k is equal to T1 plus T2 e to the power minus I k. K is it runs from minus pi to pi. It is a one dimensional Brillouin zone. You can connect it using periodic boundary conditions, but this is a very simple model which we are almost at the last stage of calculating the energy. But as we know that calculating only the energy is not sufficient, we have to also talk about the topological properties. At least first calculate the energy. And very interestingly, this Hamiltonian that we have written here, let us call it equation 4. So, the 4 and 5 combined, you can see that we can write down the Hamiltonian in terms of this called as the massless Dirac equation. And why it's called a massless Dirac equation is that usually the Dirac equation is written in terms of, so your H is equal to alpha sigma dot p plus beta m naught c square. That's the form of the Dirac Hamiltonian. And in this particular case, the Hamiltonian is this term does not arise here, and it's only this term. P is nothing but h cross k. If you take h cross equal to 1, it's sigma dot k or k dot sigma, and there is this alpha, which is usually it's a matrix in the case of Dirac equation, but here that's equal to 1. So it's a d dot sigma. So where these p is replaced by d, and these d is a function of k. So that's a vector. There is a vector, and the sigma x, sigma y, and sigma z are nothing but the Pauli matrices. So in the first course of quantum mechanics, you might have seen them and have read a lot about their commutation relations and their properties and so on. Okay, many things, and the problems concerning this Pauli matrices must have been taught. Okay. So what is this d vector? D vector has got, of course, 3 components, because we are writing it as d dot sigma, but fortunately for us, the one component is equal to 0. That means that sigma z is not there. Okay. And this is a very important thing in this study of topology, that if you have the d vector to only have 2 components, like here x and y component, but it may have y and z component or x and z component. In that case, it is easy to find the winding number. If it is not the case, that is, if you include a term, say let's call it as some m sigma z, and in that case you will have a plus, there is a m here, and this m will make the definition of the winding number to be ill defined, in the sense that you will not be able to show the winding unless you do something to the problem, that is do a unitary transformation to take away one of the components. It is very difficult to visualize the winding number. In this particular case, we will take this d vector and vary k over the Brillouin zone, which means that we change k from minus pi to plus pi, and see that the 0 0 point, see the 0 0 point when you have k equal to 0, that is, I mean 0, it means that k equal to 0. So a k equal to 0 is it becomes t1 plus t2 and 0 0. So the d vector becomes just a one component thing, which is just like a point. Okay. So this 0 point, that is the k equal to 0, which is the center of the Brillouin zone, is called as an exceptional point, and this we want to see whether the d vector encloses the exceptional point. So this is the idea, and then we diagonalize the 2 by 2 matrix, which is very easy for us to do. So this is the matrix that you diagonalize, equation number 5, fk and f star k, and then we find out that this ek is the energy dispersion for this problem, where it's square root of t1 plus t2 cos k plus t2 square sin square k, and there are 2 bands coming from the plus and the minus sign. If we open the bracket inside, we can write it in a little more convenient fashion, which is convenient for our discussion. It's a plus minus root over of t1 minus t2 square plus 4 t1 t2 cos square k by 2. And say this is equation 5, so this is equation 6, say this is equation 7, and let's call this as equation 8, and this is equation 9. Okay. So, K is, as I said, is contained in the first Brillouin zone. So, it is minus pi less than equal to K less than equal to plus pi. So, this is the form of the these Schuh-Schrieffer-Heeger model, the energy dispersion of particles in the Schuh-Schrieffer-Heeger model. It contains, as expected, the two hopping T1 and T2, and the K dependence is here, that how it varies with K, okay, and so on. Okay. So, you can solve the matrix and find out the eigenvectors as well. We have calculated the eigenvalues, and here are the eigenvectors. So, these are correspond to this plus and minus sign that you see here, correspond to the plus and minus eigenvalues of this Hamiltonian, or these energies that you see here. And so, this is equation 10, and this phi k is nothing but the tan inverse of this T2 sine k. So, this is nothing but a tan inverse of dy by dx. Okay, that is the dy means this is like a y component of the d vector divided by the x component of the d vector. Okay, it is not derivative or anything. So, this is the complete solution of the problem, but we are far from the topology that is embedded here. Now, in order to see the topology, let us examine few different cases. One of them is, let us call it as a T2 equal to 0, that is these model does not have any T2, which means that these intercell hopping is equal to 0. So, if you have intercell hopping equal to 0, it looks like this. So, there is nothing here. Okay. So, this is absent and this is absent and so on. And in this case, it is called as a extreme dimerized limit. So, these are dimers are formed, and you have a perfect dimer and there are no free edges. So, T2 equal to 0. Now, you see, if you take the other extreme dimerized limit, which means that T1 equal to 0, that is this hopping is equal to 0, if that is not there, then you get a form which is like this. Okay. Again, there are dimers, but there are two important digrations here which are not there in the earlier plot or earlier picture. Okay. So, there are free edges present, and why I am showing them as free edges is that now adding them to the system will not alter the energy, or you take them away from the system, it will not alter the energy, and that is why these are called as 0. These will give rise to 0 modes. 0 modes means with 0 energy. Okay. They correspond to 0 energy for the reason that if you take them away or put them back, really it does not make any difference. In a finite size chain, the edges or the edge atoms, whether they are there or whether they are not there, it hardly makes a difference to the energy of the system, which means that they have 0 energy. Okay. And this is what is important, that they have 0 energy, and there are other cases which are like this T1 greater than T2, that is the intracell hopping is greater than the intercell hopping. Okay. And when they are same, and when the other thing happens, that is the intracell hopping is smaller than the intercell hopping. Okay. Now, a priori, without going into the results, this case is not interesting, topologically not interesting, and it denotes a trivial state, that is like an orange which does not have a genus. Okay. This is the critical state where the system undergoes from a trivial to topological by a gap closing scenario. If you remember that we have talked about the Hamiltonian undergoes a gap closing scenario. This gap has to close and open again for the topology to be visible to us, or it's to be perceptible we can perceive it. So, T1 less than T2 is the topological state, and let us see how we understand them. If we understand them in a simple way, that is the triumph of this model. So, the energy dispersion, this is a real space for certain L, that is we have chosen certain L, some value which is say 100 or 200. So, there are these say for example 100 or 200, whatever we have say 100, and then we have solved it with T2 with T1 equal to 1. Okay. So, T1 equal to 1, you see that there is a 0 mode that is visible. Let me use a color. There is a 0 mode that is visible here. So, that is beyond 1, that is T2 greater than 1, you see there is a 0 mode, and there is no 0 mode prior to that, and this is the bulk of the system. Bulk means all the states that are in between. So, this is okay, say this is equal to 100. Okay. So, this is the last one. So, from T2 equal to 1 and above, so that is T2 greater than 1, these two becomes like this case, okay, where there are these free edges and there are 0 modes present in the system. So, there are 0 modes. Bulk has a gap in both the cases, that is the bulk states, that is these states, these are bulk, okay, and this is edge, the left edge, and this is the right edge. Okay. So, these are the bulk states which are here and here. So, the system is topological here. So, okay, because the 0 modes exist, because you can add 2 edge modes which are so it does not matter to the system whether you have added them or you have deleted them, they are the modes with 0 energy. Now, you see that before these T2 equal to 1 or larger, we just talk about, because T2 equal to 1 is a critical state, that is the gap closing thing which you see here. So, we will talk about T2 greater than 1. So, T2 less than 1, you see that there is a gap here at all values. The gap is of course reducing, but there is a gap, but there is no 0 mode. So, there is the trivial region. This region acts like an orange which has no genus, okay, and the 0 modes come from T2 greater than 1, that is T2 greater than T1, because T1 we have taken to be equal to 1. If we take T1 equal to 2, it will happen at T1 greater than 2. So, why is it topological? Because now there is a difference between the edge and the bulk, okay, and this is the precisely the distinction of topological insulator. So, in the bulk of the system, it looks different than what it looks at the edges, okay, and that is what is apparent from here. It will be more apparent if we calculate the topological invariant. We calculate the psi I squared here as a function of the site index, site indices, and you see that only at the edges, we just plot the edges in this left hand side. So, this is the edge probability and this is the bulk. So, the bulk is extended, it like a metallic bulk, okay, or they are extended states and so on, and these are seem to be sort of, there are high weights here, whereas the bulk states have almost same weight everywhere, okay. It is there is a 10 to the power minus 3, which means that it is a very small weight for all the bulk states, whereas at the edges it is almost equal to 1, which means that bulk and edge, they behave differently, and this is called as a bulk edge correspondence. So, we will calculate the topological property from the bulk properties but it will show signatures of the edge modes being present, and that's called as a bulk edge correspondence or the bulk boundary correspondence. Okay. Anyway, so we calculate this winding number. It looks a little complicated. We'll sort of simplify this discussion. So mathematically, the winding number, which is a topological invariant. Okay. So this is the topological invariant. And it's some d cap cross dk of this thing. So this ddk of this d, and then you take the z component, and then d unit vector d is the vector d we have talked about, and then magnitude of d. Okay. So this is a more useful form, and that can be used easily. You remember that we have defined f of k. F of k was defined here. Yes, this is f of k. You take f of k and take this, you take the log of that, take a ddk of that, and then integrate over the Brillouin zone, which is from minus pi to plus pi. Okay. This everywhere we have taken a to be equal to 1, where a is the nearest neighbor carbon-carbon distance or the lattice spacing. So this is, if you take this and then log of fk, you write it as this and do a little bit of algebra. This will give you the winding number to be 1 or 0, depending upon the exceptional point or the singular point is being wound or not. Okay, whether the system winds this thing. Okay, so we show all these 5 situations that we have talked about here, like the ones that are talked about. So these two dimerized limit, one being trivial, topological, and again this is trivial, critical, and topological, and so on. So we calculate this winding number that we have just defined by this and calculate it for each one of these things. Of course, this is the dimerized limit, where we don't expect any topological properties, which is this extreme dimerized limit, the top one that we see here, this one that we see here, that corresponds to this winding. So we plot both the energy and the winding number. So energy is on the left panel and the winding number is on the right panel for the same values of these things. So this T1 equal to 1, T2 equal to 0. You see two flat bands at 1 and plus 1 and minus 1, and you see that there is no winding of the d in the dy dx plane as you change k from minus pi to plus pi. Okay. As you see the second scenario, that is you have T1 still greater than T2, which means it's a trivial phase, and the bands of course show some dispersion, not like this flat ones that you see here. It shows some dispersion, but you see the winding, this dx dy plane encloses a red circle which does not include the origin, which is here. So this is of course a trivial phase, and by these blue arrows what we show is that the d vector, the unit vector d at various points in the dx dy plane as you change k. Okay, that is shown by this blue arrow here. Okay, so the winding is actually 0, winding is a point, there is no winding here. This is the d vector that is being shown. Okay, and here also it's a trivial. This is the critical. Okay, and I said that the critical will show a gap closing scenario. You see at the corner of the Brillouin zone, which are minus pi and plus pi, you see that the gaps close. Okay, gaps close. The dx dy circle just touches the singular point or the exceptional point, which is k equal to 0. So this is the k equal to 0 point, and it doesn't enclose it. Okay, and again these dx dy directions are shown like this. This will correspond to topological phase. Now if you look at the band structure between this and this, that is T1 equal to 1, T2 equal to 0.5, T1 greater than T2, the band structure is absolutely identical. Okay. So, the conduction band which is shown by red and the valence band which is shown by blue, these correspond to the plus and minus signs of the E versus K. They are different, but of course, you see the dx dy curve, which is a closed curve in the dx dy plane. As you change K from minus pi to plus pi, encloses the origin. Okay. And that is why the winding is equal to plus 1, or it is finite, okay, and it is not 0. That is what is shown here, that you see that the winding is 1 or 0. So, 1 corresponds to topological like your donut or your mug, 0 corresponds to trivial like an orange with no genus. Okay. So, even though the band structure does not say anything, that is E versus K, we have done it with Ka just to take it dimensionless so that it becomes a number, but the winding of this gives you that it winds the origin. Okay. And this is the other dimerized limit where there are T2 is greater than T1, or rather this is like T2 is equal to 1 and T1 equal to 0. That is the case which we have shown graphically by this plot, this one here. Okay. That is shown by this. Okay. Now, you see it is again topological for the reason that your dx dy plane, the curve, the closed curve actually encloses the origin. Okay. And so, this of course shows a topological phase transition as the system goes from this dimerization. So, we call a dimerization to be a ratio which is like T2 by T1. So, if T2 by T1, if T2 is greater than T1 or this dimerization is greater than 1, so dimerization is greater than 1, then topological, or let us not call it dimerization, let us call it as basically this is T2 by T1. Okay. And let us not, I mean it is a dimerized model of course. So, let us not talk about this as dimerization, but you can call it a hopping anisotropy parameter or something. Okay. So, this anisotropy, so this will be topological and this to be trivial, critical and to be trivial. Okay. So, SSH model thus encodes a very important property which is very important for our discussion. It is a very simple model, however, it shows the topological characters that we have talked about. It shows a topological phase transition as these hopping amplitudes, the ratio of the hopping amplitudes are varied across the value 1. Okay. So, we will come back with another model slightly more difficult, but nevertheless an important model which also shows topology. Okay. We will stop here. Thank you.